about what can we do by adding randomization. So we were trying to talk about like very basic deterministic algorithms, like, and also runtime complexities by using those basic approaches. And now let's consider a setting that is closer to reinforcement learning. So this is a notion called the generative model, introduced by Kakadi, I think in his doctoral thesis. So the generative model is like a simulator. Let's say that we want to solve this Markov decision problem, but the only thing we have is this generative model. So we can query, so we can ask this generative model to give us a sample transition from a specified state action pair S and A. So we choose an S and A, and the generative model draw a random sample according to the true law of transition and give us a sample. Okay, so that's the setting of generative model. So if we have such a way to draw samples, we want to know if we could develop randomized algorithms, and if randomized algorithms help at all. And further, we are interested in this theoretical question, which is, say that we don't know the MDP instance, we only have a generative model. Then how many samples would be sufficient to obtain an absolute optimal policy with high probability? And how to construct algorithms with provable sample complexity upper bounds. And a related question is, how many samples are necessary? Is there an information threshold limit to learn an absolute optimal policy with high fidelity from a generative model? So this is known as the PAC sample complexity. We want to understand sharply what is the number of queries that is necessary and sufficient for computing an absolute optimal policy with probability 1 minus delta. Okay, and this is where I need my pad. Okay. Okay, I hope this still works. Can you see the whiteboard?
Yes.
Okay, perfect. So now let's make value iteration. Randomized. Okay. So say that we start with an arbitrary V0. Okay. And we are going to draw samples. For each state and action pair, we are going to draw n samples from the generative model. Okay. And then we can compute easily the empirical transition law.
Mengdi, can you completely turn down the volume on the tablet, on the iPad? Just turn off, like, probably there is a volume control somewhere, and then you can just completely turn off the volume because there is a little echo. It's probably not as bad as my thing was, but did
somehow I can't.
Okay, fine. We can't hear you. We lost you. I don't know.
Okay, Can you hear me?
Yes.
Okay. So we have n samples from the transition law conditioned on state and given as an A, and we compute the empirical transition distribution from the n samples. Okay. So we do that for every state and action. And now given Vk, which is the current value estimator. Okay. We try to analyze the approximation error due to the fact that we're using samples. Okay. Okay. And by the way, we need, let's say that we use fresh samples for each value iteration. Okay. And notice that our value functions are always bounded by virtue of the discount factor. So we can show that this error is going to be bounded with pretty good probability. So we want this inequality, this error bound to hold for all S and A. That's why we take an additional union bound and have this ICA term in the log. And this will happen with probability 1 minus delta. Okay. So given this, we are going to use the PK hat, the empirical transition we obtained from these new samples, to get an empirical version of the Bellman operator. Okay, so the next step is we're going to apply the empirical Bellman operator to obtain the next value estimator. So we can analyze that pretty easily. We're going to use a basic triangle inequality. So we can take this error term out. Okay. Then we can see that every time we're using an empirical transition model, we're approximately having a strictly contractive iteration. And we have some estimation error, which could be bounded from this concentration inequality. So I'm going to just call it epsilon K. Okay. So we're iterating this process. And finally, one can show that. So we choose to iterate it for about this many times. Then we can show that a final error bound for this value iteration. So in this analysis, we need to make sure things are correct. For example, we are using fresh new samples for every single value iteration, so that this error recursion could hold with high probability and there's no dependence between iterations. And finally, we need all the concentration to hold across iterations. So we need an additional union bound across iterations. Anyway, so putting everything together, and we need to also choose the right choice of delta and the right choice of K. And finally, to get this final value to be close to the optimal value within an error epsilon, the sample size we need in this case is going to be and some log terms, which I don't bother to compute. Oh, sorry. So this sample size n is for every state action pairs. We need to multiply it by S and A. Okay, so this is the number of samples we need from this generative model to get an absolute optimal value by using empirical value iteration. So if we want to get an absolute optimal policy, actually we will need even more accurate value functions. So to get absolute optimal pi, the sample complexity turns out to be this. And a bunch of terms. Okay, so what do we learn from here? So apparently randomization does help. So we were talking about deterministic algorithms, and many algorithms have super linear runtime. But now if we use randomization, it's actually possible to get sample complexity to be linear with respect to S and A. And if we try to make the algorithm update in a smart way, it turns out that we can actually make the sample complexity to be equal to time complexity. Okay, so we can get O1 time update per sample. But however, we can, if we try to look at analysis, so the analysis turns out to be pretty simple, but we don't really like what happens here. Okay, so this is 1 minus gamma to the power of 7, which is a big number. So what's happening is the analysis we just have here is okay, but it's not good enough. So it's not good enough in several different ways. So first, the algorithm itself is not the best algorithm. We can see that the algorithm takes fresh new samples per each update to make the analysis simple. But however,
Mengdi, sorry to interrupt. The powers on your 1 minus gamma are not readable by people. There are several questions about what are the powers on 1 minus gamma.
7.
Oh, and in the expression at the bottom of the page?
It's 5.
Thanks.
Okay, yeah, thank you for the question. Okay, so basically we lose some factor by rounding an approximate value to an approximate policy. So the power is raised from 5 to 7. Okay, so those powers are not good because first, the algorithm is drawing fresh samples per iteration. And we don't really need so many samples per iteration if we have to throw them away immediately. So we're not utilizing samples in a very good way. Another problem with analysis is when we try to analyze this error recursion, if we just analyze the error recursion in the L infinity norm, so this epsilon k just becomes a worst case upper bound. And then what happens is we are just being too pessimistic in every single error bound. What's really happening is it's possible that the accumulation of errors throughout value iteration somehow have its own statistical property. So the error actually doesn't accumulate so fast. Okay, so I'm not going to talk about how to improve this to get a final result because that's going to take hours. But basically, it's possible to use samples in a way that's smarter. And also, it's possible to do the analysis better if we really try to delve into the noise structure and how the noise accumulates in the computation process of the estimator. Okay. So I'm going to go back to my slides. Okay, so basically one can make value iteration work even with only with samples from a generative model. And if we try to be careful with analysis with the algorithm, it's possible to accelerate it. Okay. So next, instead of doing value iteration, one can try to do Q iteration, which has a number of advantages. So Q function can be viewed as a value function for state action pairs. So we associate each S and A with a value, and then we get Q function. So we can write down Bellman equation equivalently in the space of Q functions. Okay, and we can also have a Bellman operator for Q functions, which we call it F. And it's pretty straightforward to see that Bellman operator in Q functions works very similarly as if it is Bellman operator in value functions. And Q iteration has similar convergence properties as value iteration. Okay, but however, there's a very nice property about Q function. What's happening is if we look at the Bellman operator in Q functions, it takes the form of an expectation. So that makes it possible to solve this fixed point equation by using stochastic approximation. So that gives rise to the Q learning algorithm, which is nothing but a variant of stochastic approximation for solving the Bellman equation in the space of Q functions. And it allows us to get an unbiased estimator of the Bellman operator applied to Q functions from a single state action state transitions. Okay, so by using analysis for stochastic approximation for root finding, one can almost show convergence of Q learning algorithms under some proper assumptions that the data generating process has to be ergodic and visit all the state action pairs sufficiently often. Okay, so there's a much richer story of Q learning if we talk about sum complexity and regret analysis, but that will be a topic of future talks in the program. Okay, so finally, we can also use randomized algorithms to solve the linear program of the Bellman equation. One particular thing to notice is the linear program of the Bellman equation has a primal form in the space of value functions and the dual form in the space of occupancy measures. So it actually is also equivalent to a saddle point in which we have a nice strong duality between the optimal value function and the optimal stationary occupancy measure under the optimal policy.
Mengdi, sorry, Ambuj again. I think the slide issue of them not advancing has happened again.
Okay, let me do it again. Can you see it?
Yeah, now I see a slide with title from LP to Bellman saddle pulse.
Okay, that's correct. I think I should update my Zoom. Okay, so the Bellman equation corresponds to linear programs, which corresponds to a nice minimax problem in the space of value function and occupancy measures. So it turns out that one can use approximate LP methods for solving Bellman equations. For this, one can try to do constraint sampling to solve large-scale linear program, which in the language of reinforcement learning would mean that we simply sample transitions from a subset of state action pairs, which would mean that we sample a few rows from the collection of linear constraints. Another approach is we can directly try to solve the minimax problem by doing some form of primordial mirror descent. So basically to do descent in the value space and ascent in the opposite measures. And there are several works along this line. Okay. So finally, we want to think about the question, so is there an information direct lower bound? So how many samples are at least needed to get a good estimate of the near optimal policy? So there was a very nice lower bound result proved by Azar and a few others in 2013. So they constructed an MDP instance such that any algorithm, no matter how smart the algorithm is, has to make so many queries to the generative model in order to compute an epsilon optimal policy with probability 2/3. Okay, so let's look at this lower bound. So this lower bound is linear to the number of states times number of actions, which is what we expect from the earlier analysis from fitted Q value iteration. And now if we look at the power in terms of the power of 1 minus gamma is a power of 3. So it's much smaller than our previous analysis. Okay, so I originally planned to actually give a sketch of the proof, but I think my equipment is not functioning optimally today, so I'll skip that. So basically, the idea of the proof is to construct a particular instance such that finding a near optimal policy to that MDP would require testing a particular Bernoulli variable. And the instance is constructed in a particular way that there are many different potential hypotheses. For example, there are S times A number of choices for the Bernoulli variables to have a slightly higher probability P than all the other variables. And then any algorithm has to sample all of the state action pairs for enough times in order to tell which of the state action pair corresponds to a Bernoulli variable, which is slightly different from all the others. Okay, so that's a very cute proof, but I'm not going to do that today. Okay, so finally, my last slide. So this is my current knowledge about the upper and lower bound for planning in MDP under a generative model. So the lower bound is the one I just described to you. So one could construct a particular problem to show that it's fundamentally about hypothesis testing and estimation. And the sample complexity lower bound is this. And it turned out that there actually are algorithms that could nearly achieve this lower bound. So one algorithm is actually an improved version of empirical value iteration. So like I have described, so the simple value iteration I described was inefficient because we are taking new samples per iteration and we are throwing them away for simplicity of analysis. But if we care for doing a bit more analysis, we could actually do variance reduction and show that the algorithm actually concentrates much faster than we expect. So it's possible that a form of value iteration achieves the lower bound. And another recent result is one actually shows that it's actually possible to achieve this lower bound by simply estimating an empirical transition matrix from data and then just use it to get a plug-in estimator. So that's an even shorter answer and a very elegant method. So in short, basically now we know sharply what is the theoretical limit and what's achievable for planning in MDP under a generative model. And the upper and lower bounds are nearly matched. So that's it for my part. Thank you very much.
Mengdi, someone asked, what's the reference that you referred to as Jin and Sid for 2020?
I think that's Aaron Sidford's recent ICML paper. So one can find that on ICML 2020. I think it's called like solving MDPs using stochastic mirror descent. But I don't know whether it's on arXiv yet or not, but it's already published by SML.
Okay, thanks.
Okay, thank you.
Right. Let me see. I need to share my screen here. Thanks, Mengdi. All right. Good. Wow, my screen looks completely distorted. Is it the same for you guys, or?
It looks fine on our end.
Okay. Okay. I just had to. Yeah, I'm connecting with two computers and one of the computers, so that was different proportions, but now it looks good on my computer too. Okay. So in this last part of the morning, I'm going to talk about how to scale up things. And Mengdi started to mention a few things like approximate linear programming and whatnot. So this is really important. Oh, by the way, no one really asked the question, why are we doing all of this? I guess there is reason you want to use planning methods with model-based reinforcement learning. You're learning a model, and then you need to find out what an optimal action is, or given the model. So that's one reason. Sometimes you just build a simulator, and then you believe that the simulator is pretty close to a real system, and you just want to know how well you could do and what action should be taken. So these are the reasons. Many times, anyways, what happens is that, well, okay. What happens is that these MDPs are really, really large. And so the lower bounds that Mengdi mentioned show us that, well, if you have a big MDP, that means that you have a large number of states. And here I'm abusing notation by not denoting the coordinate of the state space differently. I'm using the same letter for the number of states as this, the set of states. Apologies for that, but I just want to minimize clutter. Same with actions. So if you have either large state or action spaces or horizon or whatnot, but it seems that you're toast with these methods that try to compute an optimal policy because of the lower bound. So this is an actual barrier, right? So if you're demanding that you have a planning algorithm that takes these inputs and or interacts with the simulator, and in all cases is able to produce correct answer, then you're gonna see these lower bounds and kicking in, and which means that it's not that we are lame and we can't find good algorithms that would solve these problems fast, but these problems can just be really hard. Okay, so maybe you need to look at every possible state and action. It's not hard to imagine that this should happen in the lack of extra structure, for example. The question is, what can we do? Because in most interesting examples, the state space tends to have a factored structure with D factors, so that could be the dimension of the state space. And the D can be really hard, so really large, so the number of states could be really large, or you could even consider continuous state spaces like the hypercube. And so the state space in all these cases is really, really large. It scales exponentially with the dimension. And so that led to people calling the phenomenon that the algorithms, the vanilla algorithms, break down as the curse of dimensionality. But just because we see these barriers, we never stop. We won't stop. But instead, what we need to do is that we need to change the problem, right? So maybe the original problem setting was not the problem setting that we really need, and maybe we can just change it a little bit, and then we can solve some variation of the problem, in which case we may be able to overcome this computational or query complexity barrier. So here I'm going to talk about 3 ideas. The idea of localizing planning. So I call this local planning. So previously we were talking about that you need to calculate the policy that is basically a big table of at which state what action to take. And you can imagine if you have many states, then even filling out a table like that is not feasible. But for example, if you're in model-based RL, you are at a state when you're trying to use your model that you learned in some way, and you just need to figure out what action to take there. So that's local planning. So that's the first thing that I'm going to talk about. And then there are 2 other things: extra hints, very functional approximation and policy search, or assuming extra structure. So for this latter, I'm not going to talk much about it. There is a lot. There would be a lot to talk about it. I'm just going to illustrate it by an example which is quite popular these days and has been popular forever. So this is the case when you have maybe vector valued states. So the state space is r to the power of d, let's say, and the action space is also a Euclidean space r to the value of, I don't know, k or whatnot. And the state evolves according to this dynamics here. So the next state is matrix times the previous state plus matrix times the action taken and some noise on the top. So this is called a linear dynamics. It's linear both in states and both in the actions. And the noise could be just IID Gaussian noise. And the reward could be very nice, like the negative of the quadratic form online state with a positive definite matrix Q, and the same with the actions with a positive definite matrix R. So this leads to this class of problems called the RQR problems, and they have such beautiful properties that it becomes feasible and tractable to find an optimal policy as a function of just these matrices A, B, and Q and R, right? So here, everything that you need to know about a system is just summarized by these 4 matrices. So the planning problem becomes how to use these 4 matrices to come up with an action that an optimal policy would take. All right. So that was just to illustrate that you could have some extra structure that helps you deal with really large state and action spaces. So let's return to the other 2 points. So local planning. So let's start with that. So what is first of all, what is local planning? By the way, is the sound and everything's fine? I hope that it improved. So in local planning, as I alluded to, your input is a little bit different than as usual. So you're given an initial state, and you have maybe a simulator access to the MDP that Mengdi was also talking about, and the output that we require the planner to produce is just an action. Okay, that you should imagine that this process is repeated. So as state is inputted to the planner does some computation, access the MDP a few times, it produces an action. and then this is repeated for the next state and the next state and next state. You could do this online. And if you do this online, this results in a policy. So a planner that does this local planning implements a policy. Maybe it's a stochastic policy, because I mean, the simulator is randomized in general, so the action is going to be random. So we can collect or summarize the distribution of this action given the initial state, and that becomes a policy. And so here the job of the planner is to come up with a procedure that produces actions from an underlying, perhaps implicit probability distribution pi, such that the induced policy is going to be near optimal up to a level of delta. All right, so that's the goal. So the idea here was that we don't need to fill out a big table of like what these probabilities are or how to choose at every given state the action, but we can do this calculation on demand. Computer decided to go to sleep. Let me see whether I can give it some boost. All right, I just need to do this time to time. Just touch this computer. Okay, so this is the goal. And so we are amortizing computation. And so you can save a lot in this way. So for every state, we can query the MDP, we can perform some computation to produce the action. Altogether, if you have many states, then altogether you may be doing, infinite amount of computation after visiting infinitely many states. So here, computation is budgeted in a different way, per state manner. So this problem may be easier. So maybe this way we can overcome this challenge that that is posed by the lower bounds that would tell us that you need to depend on the coordinate of the state space. And lo and behold, that's true. And the idea is actually quite simple. So recall the notion of effective horizon. So when we're doing planning, if we want to produce a delta optimal policy, then we can cut the trajectories at maybe delta or delta over 2 level, effective horizon level, which would be just is log 1 over epsilon 1 minus gamma divided by 1 minus, sorry, that's a delta, divided by 1 minus gamma. And then use this with delta equals, I don't know, delta prime equals delta over 2. Because if you're cutting the trajectories, then like you don't like infinite trajectories because that would mean infinitely many access to the MDPs and infinitely lengthy computations. But you can think about cutting trajectories after this many steps, and then build a tree. So you're given this initial state S0, and let's say you have just 2 actions. You take action 1 and you take action 2, and then you sample from the dynamics a few next states. So these are the next states, and you're going to sample M next states. And then you continue for each of the state encountered. You take first action, you take the second action. For each of the actions, again, sample a few next states, let's say M of them. And you do this tree building for a depth of h of delta prime, okay? And so the question is, okay, what does this give us? Well, what you can do is that you can view this as a way of, approximating the original MDP. In the original MDP, if it was a finite horizon MDP, and these were the actual next states, and there would be no other next state, then you could just do a backwards calculation from the leaves, and you would just, like sum up the rewards, and so that would give you a value at an action, do it for both actions, take a max, sum up the values again. So this results in a value of the state. Do this for all the other states. Take the average of them. So not summing, but taking the average of them. And then the average is assigned to the action. And then do it for both actions, take the max, and so on and so forth. So you can do this backwards calculation. And if you get to the root and you see that, one action has a higher assigned value to it based on this calculation than the other action, then you would just choose that action. And the only question is this going to be a faithful representation of the full MDP? How big should be M? To get a reasonable estimate for the values here. And in order to do this calculation, I'm not going to do it, but just to note that, averages concentrate pretty fast. And here the idea is that we need to calculate, these expected values based on next state distributions. And we just sample a few next states. But we are using this in a lot of calculations, but only finitely many calculations because we have a finite horizon. So this tree could be big, right? So it's going to be at least 2 to the age of that size. But we also know that we can use union bounds, right? So if we want that all the averages that we calculate with high probability represent the true averages, we can use union bounds, and we don't need to use too many union bounds. We need to use roughly this many union bounds, that those go into the log. When they go into the log, then H becomes, so this M, which roughly should be the log of the number of different cases that we need to consider to control for error probabilities in all those cases. So that's what the union bound is doing. Then the M that you need to take is going to be linear in the horizon. I apologize for the background noise out of my control. All right.
Csaba,
yeah.
Just to make sure people don't think they're on a slide that's behind, like, could you maybe just, oh, okay. So right now what I see is a right panel that says afterlife.
Yeah, it's fine. I guess I made a mistake that I was pointing a lot, and the pointer is not shown. But basically, I was explaining backwards calculations on the tree, and then I just added this little calculation here with the union bound at the bottom. So I hope that that's clear.
Yeah, I think we're good. Thanks.
Okay. All right. So based on this, if you do the calculation, then you can prove this theorem. And this is from a paper by Kern-Swanson and Wang from around 2000. And this is called the sparse trajectory method. And this shows that these many queries, A is the number of actions, H is basically 1/1 minus gamma. So A times H divided by data, that is the required precision to the power of H. So that's kind of the size of the tree that you're building. So these many queries are sufficient to get data optimal actions with high probability. And they also prove a lower bound that without making any further assumptions about the environment, the MDP, or changing the problem, they show that the exponential dependence on the horizon, which looks really unfortunate, is unavoidable. So at least 2 to the h queries are necessary. Obviously, there is a gap between the lower bound and upper bounds, and it would be interesting to see how to fill that gap. But this is what we know so far. But the important thing here to note is that by changing the problem to local planning, we managed to avoid dependence on S. So there's no dependence on S. And then you can have variations. You can do this for PUMDPs. I won't go into the details. In PUMDPs, you would have these deterministic policies that take past observations. In this case, the trees become extremely sparse, only one next state, but you're going to have many trees sampled. But it turns out that you don't need too many of these trees. So given such a tree and the deterministic policy, a tree gives you some value estimate for the policy, and you can just take the averages across these trees, and you can recycle these trees to avoid many policies. If you have finitely many of them, then the log number of policies is going to appear in how many trees you need to take, and more generally, the VC dimension or other like complexity measure of the policy class is going to appear. So this is about local planning, and here I added another note about that this has a rich afterlife. So you may notice that these trees are uniformly built, and even if the MDP is super nice, these methods are not taking advantage of this nicer structure. So Remy and other people, including myself as well, spent quite a bit of time of trying to figure out how to take advantage of the nice structure of MDPs. And Remy wrote a very nice, Remy Munoz wrote a very nice monograph that I can only warmly recommend for everyone. So it's in the Foundations and Trends in Machine Learning. So that much about local planning. So local planning could also be applied to this situation, though, that Mengdi mentioned, where you have continuous MDPs and smooth transitions. And if you do this, Joan Ross noticed this, and I worked a little bit on it, you can overcome this 1 over epsilon to the 2n plus m. Lower bound will be gone, and you can have an algorithm which is fully polynomial in all the relevant quantities for the same class of MDP. So changing the problem is if you don't need to solve the harder problem, why would you, right? Like it's a good idea to change the problem. All right, so what's the other idea? So the other idea is to add extra hints and structure. And here, one of the things is to consider value function approximation. The other is policy search. So the last result that I just mentioned for PUMDPs was basically a policy search result. It says that you can uniformly well approximate the values of any of the policies. And if you are able to then search the space of policies in some efficient way, because maybe the policy space is structured in some way, then you would be done. Unfortunately, life is not so nice. Actually, it happens that computation becomes more often than not really hard. So if we phrase this problem, this policy search problem, that such that given a policy class of, let's say, stationary policies, then finding the policy that maximizes the value given initial state efficiently is going to be NP hard. And this is based on a paper by because Wass is Michael Liedman and Barber from 1220. I'm going to add pointers at the end to the slides, and I will make the slides available. So don't worry about those for now. So that's one way. Sorry, so that's bad news actually, right? So NP hardness tells us that this is not going to fly unless you add some extra structure. And if you have the extra structure, how are you going to search? So one idea is to use some local structure. Maybe you have a parameterization, some policies, so you have a parameter space, and these parameters live in RD or whatnot. And you go from the parameterization to this parametric policy class that induces the occupancy measures. And if you take the inner product with the occupancy measure and the reward function, then you get the values. And so you have this composite map where you go from parameter to policy to occupancy measure to value, right? So this is real value at the end. So you go from RD to R. And this part is very nice and linear. This part is, this depends on the transition structure and somewhat nice. So if you had the full policy class, policy iteration, whatnot, it's really nice to search it sometimes, but not always. And this could be nasty, but together these two guys could be nasty. So that's kind of the issue here. So that's why you could expect to see in the lack of extra structure some hardness results. But okay, so let's say we still want to go with this idea of local search. Maybe we are just happy with some local search algorithm that finds a local maximum. Can we even calculate the gradient here, given simulator access? And the answer to this in a nutshell is that yes, we'll be able to do this. And this is based on the so-called score function method. Which has a long history, has been rediscovered, I think, a couple of times. And I believe that maybe on the day when we're going to have the talks from the OR perspective, we're going to hear from Peter Glean, who is one of the original authors of this, together with Ronald Williams, who discovered it independently for MDP. So, so how do we do this? So the idea is that you have this derivative that you want to take, and you can maybe assume some regularity, and then you hope that you can move this behind the sum. And then we need to take the derivative here. And the observation is that if you take the derivative of the log of this probability, then that will become the derivative of the probability divided by the probability. So if you multiply with the probability, pre-multiply with the probability, so then these two guys cancel each other and you just get the derivative. So basically, this derivative here is equal to the product of this probability and the derivative of the log. So this is called the score function. And in some parts of the literature, it's called the score function method. And if you do this, you find that, okay, so we can write this as an expectation. So the probability distribution P of pi of h is kept of the gradient of the log of the same thing times R of h. Okay. So it remains to calculate the derivative of the log. And so here, the thing to notice is that this probability, the probability of a trajectory, the trajectory has all these states and actions in it, is just a long product that I mentioned before. And then the product previous and so on and so forth. And if you take the log, this becomes the log of the sum of the logs of the individual terms. And the transition terms don't depend on theta. So theta is the parameter of the policy. So P doesn't depend on theta. So that's very handy. And if you're taking the log, you're taking the derivative, then you will find that only the derivatives of these guys, the logs of these guys, will show up. And so you can plug that in, and then that's called the score function method, the reinforce method, and so on and so forth. So notice what happened here. So we constructed an expression for the gradient, which is written in the form of an expectation. But of course, we can't compute these expectations. So we would be using sampling. So we would sample a trajectory from this policy pi and calculate this expectation as a sample average, maybe a bunch of trajectories, and then take the sample average of them, which is one of them. And what's true for this estimate, this random estimate, is that it's going to be unbiased if everything was nicely controlled. I mean, if these quantities do exist. So this is an estimate. This is a random estimate. So it's going to have some variance. And lo and behold, there are many other ways of constructing estimates. So people write lots of papers about how to reduce the variance. There are many, many different estimators. These days, another topic that rapidly gaining attention is to study the global convergence of these methods. It's really interesting that many cases we can find conditions, sufficient conditions on the policy parametrization such that global convergence holds, and people are trying to nail this down and even getting results for the rate of convergence. Fortunately, don't have time to go into this, but I will add pointers to the literature. So with that, I'd like to move on to the last part. I'm already running a little bit late, sorry about that. Which is to use extra hints or structure in the form of value function approximation. We're going to see a lot of value function approximation later on, but just to give you an idea, so here the hint, the extra structure that is assumed, is given as a set of either state value functions or state action value functions, and oftentimes they do have a linear structure. So here phi, you can imagine as a big matrix, S was finite, so it has as many rows as the number of states, and as many columns as the number of features, and so the rows of this matrix are the features. And the assumption is that these features are available by random access to the planner. And again, you would consider either localized or global planning. And the hint is that this function space captures the belief that, let's say, Q star lives close to this function space, or it is actually in this function space. If it was about state action pairs. If it's about states, then V star lives in this function space. Or a stronger assumption is that Q of pi for all policies or stationary Markov policies pi's lives in this function space. Or you could do the same with state value functions as well. And if the belief is correct, then we expect to be able to replace inner complexity bounds and query complexity and computation complexity bounds, the number of states expected to be replaced by the dimensionality. So it accounts for basically compressing the states or abstracting the states. So you might ask whether this is a sneaky assumption about MDPs, and yes, you could see it that way. And we can even try to make this explicit, and so this became quite a hot topic recently. So if you want to make it explicit, so there is one set of assumptions that give you some really nice conditions under which some really nice things happen about the MDPs. And this goes as follows. So we're going to call a transition dynamics linear in some feature map. So for every state action pair, you get a bunch of features. If there exists another map which maps from states to RD, such that for all states, actions, and next states, the probability of arriving at the next state is the inner product between the feature and the value mu takes at state S prime. This is a factorization assumption. So if this factorization happens to the transition dynamics, then a lot of other nice things happen. So to make things even nicer, we may assume that the reward function is also linear in the features. So that means that RSA for every SNA is just phi SA times, I don't know, lambda, where lambda is. So there exists some lambda which is independent of SNA, such that this holds for every SNA. And if P and R are both linear, then we call these linear MDPs. So this was introduced by Chi-Chin and others. And so the claim here, which is going to help us a lot, is that if P and R are linear, then for every policy, every station Markov policy, Q of pi is also linear, which is easy to see if you think about what happens with Q of pi. It's the fixed point of the Bellman operator. And in the Bellman operator, you have basically the reward plus gamma times the transitions, and the transitions, if you wish, you can write it as this factored form times somehow applying pi to q, just introducing random notation here. So they're just a state value function created from the state action value function q of pi. And so whenever this applies, you can use associativity, and you see that, like, okay, this is equal to phi lambda, and this is equal to phi times mu and some stuff. And so the whole thing becomes can be written as phi times theta with some theta that depends only on the policy. And so this gives you the idea that if you have a linear MDP, then you should be able to work just in the parameter space and run a policy iteration algorithm. And lo and behold, you can do that. And if you do that, then you can get fully polynomial algorithms under this condition that you have these linear MDPs with the truncation and contraction arguments. You can make this work. I'm going to give pointers again to the literature at the end. But you might worry about that. Okay, so here basically what we are using is that Q of pi is in this linear space, and this may be a little bit too strong. So what if Q of pi only lives close to this space? By which I mean is that if you shift Q of pi a little bit, then it becomes an element of this linear space. So this Z is this error function, and the error altogether is not big, it's an epsilon. And you might think that, okay, if you have a robust algorithm, then it should be able to survive small changes to a problem like this. The question is whether this happens or not. So the surprise comes from this recent paper by Kakadi, Wang, Young. They basically show that this doesn't happen if you want a delta optimal action with delta that is proportional to epsilon. Then you can't do that unless you query. Basically, you have this tree, and you have to query exponentially many states. So basically, you have this tree, and it has 2 to the age leaves, and you can hide the reward there, and the features are not going to help you. The Johnson linear shows lemma is used in a very nice and elegant fashion to show this result. So the question is, okay, where do we go from here? Well, the lesson here is that if you demand too much, then you're going to suffer. So high precision maximization with approximate models is going to be super expensive. So if you just need to solve, need to find, the input to a function which is nearly linear, but the function is over a space of many elements, like the leaves in the previous example of the tree. It has many elements. Then the number of queries that you're going to need, if the function was epsilon close to the linear space and you require precision of delta, is going to be exponential in d times epsilon over delta squared. And that's bad news if you want high precision. But you may also notice that so delta is the desired precision. If we make the delta a little bit larger, so square root d times epsilon, then this hardness, lo and behold, goes away. You can use many different tools to show this. We use the Kiefer-Wolfowitz lemma in a recent paper to show that this is the case. So here the lesson is that, okay, maybe don't demand such high precision, and then you'll be fine and you can get polynomial time results. This still leaves open the question of what happens if we make a weaker assumption, right? Just like the optimal action value function lies in the function space or close to the action space. We don't quite know the answer to this. So with this, I'd like to conclude the morning, and I'll apologize for running a little bit late. So we were talking about planning given a model, which is the problem of finding either a policy or an action given an MDP under different access models, simulator access, or this tabular access if you have finite MDP. And different variations of this planning problem, local versus global. For finite MDPs, I would say that we have a near complete story of understanding at least the discounted corner of MDPs. There are unfinished cases in other challenging versions of MDPs. And for large MDPs, the ideas we looked at were local planning, computation with hints, value function hints, or policy search hints, and under these conditions, sometimes we can say positive things, but there are many open problems left. And another direction that was briefly mentioned is that you can have just a favorite MDP class, and of course you could have a combination of all of these things. And it's fascinating because there's so many open questions still exist today. So with that, I'd like to conclude, and we'll leave you to have lunch. I'll be around. I'll be on Discord, and I guess Mengdi is also going to be there. So I recommend that we somehow channel the questions related to these talks to Discord, and I will upload to start with my slides there just a little bit later because I have some errands to run now. And so let's have the discussions there. So thank you so much. Right. Oh, okay. So there is a question about what is Discord. Discord is like Slack, and there is a dedicated Discord server. Oh, where is Discord? Okay, all right, good. Can someone help me to paste the link here? Anyone who registered should have received a link to the Discord server, but if you haven't received it, then maybe we can. Okay, so we have the Discord link here. All right. Okay, I also see some, I don't know. Are there any other burning questions that I should ask before we go? Thanks everyone who were answering the questions in the background. Right. All right. Then see you guys around.